like that, right? We were shooting cannons. Okay, and we established a couple things, right? We established that we'll come back to our competition again later for another Friday football fun or Thursday football fun or something like that. But we established that. Can you translate me back this question? That was the one thing. Like skip. Oh yeah. There you go, right there. So we established that there's an independence here which is very useful. Right, if I shoot a cannonball up in the air, tell me about its motion. It's a parabola, okay? That's, for the moment, we don't care about that. Okay? Eventually that'll be useful to us, but for now, just talk to me about the motion. Why is this motion not as complex as it looks? What are we able to do?
It's symmetrical.
Okay, it's symmetrical. It's symmetrical, sure. But what are we able to do to because the cannonball is simultaneously moving up in the air and moving down range, which creates this complex parabolic trajectory.
You can treat the height and the distance as separated.
Okay, we can take the horizontal and vertical components, right, and treat those separately. And that makes things pretty simple, right? Because then the vertical component looks just like, well, in fact, we could even calculate this. So the vertical component is going to look just like, who's got a calculator handy? Somebody? Real quick. Somebody got a calculator handy? Got one? Okay, do this for me. Make sure you're in degrees mode. And I would like, actually, you don't even need to do that. I'll just tell you what to do. So you're going to multiply 18 by the square root of 3 over 2. Okay, what is it again? Oh, hang on. No, it can't be. So it's got to be less than 18. 18 times the square root of 3 over 2.
It's 15.5.
About 15.6? Okay. So I want you to see something there. So watch. If I fire this again, watch what happens. There's my projectile. Let's erase the trajectory. And let's make this something big like a cannonball so we can... Actually, let's make it...
Pumpkin. Adult
human. Okay, so there's our adult human being shot through the air. Now watch this. I want you to notice if we go at an angle of 90, and it was what, about 15.6?
Yeah.
Watch this. How long is it in the air? 3.3, same amount of time, right? Point being that what we just did a second ago is the vertical component of the horizontal motion, right? But how far are we actually going down range in that time? Well, if we shot this thing at a 0-degree angle at 9 meters per second, it's not going to go anywhere because it's just going to fall right there. But if you slid across the ground, I guarantee after 3.3 seconds, that person would be right over there. Agreed? And that's what we learned, that we can split this up into horizontal and vertical components and treat them separately. What connects them? Well, the fact that it's the same object connects them. So that, for example, the important events here, like when the person is shot out of the cannon and we start the stopwatch, that's happening to both the vertical component and the horizontal component at the same time. The person is going to reach the apex here at some interesting time during the flight, and whatever that time is, we'd have to look on both the horizontal and vertical parts of the motion to sync those up and see what's going on. Right? You can tell me what's going on at the halfway point. So at 3.3 divided by 2, which is about 1.65 seconds, what's going on vertically? He's at that point right there, where I'm pointing. See my little pointer up there? I'm right at the apex. What's going on vertically at that point? Try it again. Oh, what happened? Oh, I changed the speed, didn't I? It's when he stops moving vertically, isn't it? So right at the top, that would have been just halfway, wouldn't it? Okay. What's going on horizontally? Pretty boring. It's got constant speed the whole time. What's happening over here at the very end at 3.3 vertically? That's when he's getting back to the earth, right? Okay, we'll come back to this. We took an example of a fairly complicated example of two-dimensional kinematics, but we can see that we're greatly assisted by breaking up the motion into two components. Okay? Now we're going to leave this for a little bit, and let's go back and let's look at this kind of graphically. Let's look at this in terms of the vectors. So would everybody agree that horizontally, if this is the cannonball that's being launched out of the cannon, this is the pretty boring horizontal story. The vectors are all pointing in the same direction and they all have the same magnitude, right? Constant horizontal motion. Why is that, you suppose? Just thinking way ahead here. Why is it not accelerated horizontally? Because the only acceleration is coming from gravitational acceleration, right? And that's vertical, okay? Seems like a pretty dumb question, but there's actually something pretty significant about that we'll come back to here in a second. So does everybody agree then that this would be our vertical story? There's our initial pretty large velocity, right? With time, though, if these are uniformly taken snapshots in time, then each time we go up a little bit, the vector is decreasing a little bit. It gets to its highest point where the vector has a magnitude of 0, and then it picks up speed on its way down, right? And if we were to sync up, does everybody see here also that like technically we color code these things, like this one should go with that one, right? And this one goes with that one, etc. Right? Those are just like a strobe photography, and each picture of the cannonball lines up a horizontal and vertical component. If I randomly took just one of those pairings, it might look like this. Okay? I've got my horizontal component and my vertical component, and this is the part I want to kind of start to look at today. Does it make sense that if I combine this blue horizontal component with this orange vertical component, I'm getting the purple resultant if I combine both motions at the same time? Yes. Okay? That tells us something important. That tells us that when we want to add vectors up like this, we always add the vectors tip to tail or head to tail, whatever you want to say. We're going to take the head of one vector, and that has to coincide with the tail of the other vector, or tip to tail is what I've always said in the past. Our book, the OpenStax book, says head to tail, so I'll say that too, right? Okay, that's how we combine those vectors. If we want to look at a picture of the whole motion then, where we're going to combine each snapshot of the cannonball, it's just going to look kind of like this, isn't it? The initial launch angle is up at like about 60 degrees in this picture, roughly, let's say. So in that case, it must have a larger amount of larger vertical component than horizontal component. At some point, we're going to be at about a 45 up here, right, where the components, the vertical components diminished a little bit and the horizontal component stays the same, but they're the same, right, at that point. So we get a 45-degree angle for our velocity vector. At the very top, the vertical one's gone away, and so the velocity vector is horizontal to the right. We see that, and then we're just going to reverse that process, right? It should be symmetrical. So notice that if this was our 45-degree snapshot on the way up, then that must be our 45-degree snapshot on the way down, right? Only now the angle is negative 45 instead of positive 45. Yes?
With the horizontal, after it reaches 0, the ball is left to fall.
No. If we're ignoring all the real-world stuff, so there's no friction acting, horizontally there's no, and I'm throwing out some words that we haven't talked about yet, but in the near future we'll talk about this in terms of forces. And one of the things we're going to say, and I'm going to say it now, we'll say it again later, is Newton's first law is the law of inertia. which just tells us that an object in straight line motion tends to remain in straight line motion with constant speed unless acted on by an external force, right? And so, technically speaking, yeah, if this were infinitely high and the gravitational field were uniform, it would pick up more and more and more vertical speed, but the horizontal component would always stay the same forever and ever. Okay? Kind of get a sense of what we're doing with this? Okay, so we'll come back to this when we've got a few more tools in our tool belt. For now, we're going to look at something a little bit easier. Okay, so now let's take several steps back, and let's look at how we can deal with combining position vectors. Okay? So what if we want to start here in this town, and we want to walk due east for 9 blocks and walk due north for 5 blocks? Okay, because we're not going to trespass. We're going to walk only on streets. Now, we could, if we wanted to, I suppose, we could take kind of a zigzag pattern, but assuming that we're going to be efficient about this, we're just going to travel to the east first and then north, right? Let's say that we had access to let's say a helicopter, but that's too boring. It's going to be a jetpack, right? If we want to go from the starting point to the ending point, and we now have a jetpack, so we can be above the city blocks. Obviously there's a shorter distance here, isn't there, for us to walk anywhere. Well, of course, what would I do in that case? I'm just going to go straight diagonal, right? So we could do something like this. Right? And get there more quickly. Okay? So would you agree that this vector represents my final position? How come? What does a position vector do? Position, we said, is a vector quantity because it has what two kinds of components? What are the two parts of any vector? Direction and magnitude, right? Magnitude is going to be the number. Direction is going to be direction. And so if we end up right here, if we want to write our final position as a vector, we have to know two things. We have to know, okay, relative to where we started, how far away are we, first of all, right? Which we can calculate. We also need to know what is the precise direction. Now, we don't yet have the toolkit to, some of you actually do. Some of you, if you've been through trig, you might be able to answer this question right now. Okay? If you haven't, you won't for sure. And even if you have, this may not be an application you're familiar with from trig. But we're going to do some trig. That's how we're going to add these things up analytically. But we're going to call this some angle theta for now. We're just going to define some angle theta. And we ought to be able to figure out what's the direction relative to due east, for example. How many degrees above north of east are we traveling at, and how far did we go? And that's kind of our goal. It's a short day today, so I don't know if we'll get through all this today, honestly. But that's our goal by, like within halfway through the period tomorrow, let's say. We want to be able to get to that point. Okay. Well, we can find the distance pretty easily. You can all probably tell me what to do. If I want to know the length of that final position vector, what's the math involved with that? Pythagorean theorem, because it's a right triangle, right? Because my two components of my motion here are perpendicular to each other, the two vectors, right? Everybody agree? Okay, so we could say the length of this vector is what then? The square root of what? So looks like we went 9 down here, right? So 9 squared plus 5 squared. So square root of 81 plus 25, what is that, 106? And that's an exact answer, right? Okay, so that's the distance that we traveled. So that's roughly equal to about, what, 10 point...
10 and a half.
Yeah. Maybe, yeah. Let's see, what is it again? 10.3-ish. So 10.3 blocks. Okay, and so pretty soon we'll be able to use some trigonometry to figure out what this angle is, and we'd be able to come up and say, okay, so our final destination is 10.3 blocks at an angle of whatever, say it's going to be about 30 degrees north of east. Okay? Piece of cake. It can get a little harder though. What if we want to do one like this instead? Actually, I'll go back to that picture. What if we want to do something like this? What if we want to, so there's what we got, right? Okay, what if we want to do this though? Now we're going to be lawbreakers. Okay, so this time we're going to do something different. We're not going to go by the purple vectors. This time we're going to end up, this is the trip we take. We're going to go 6 blocks this way, and then we're going to do something terrible. We're going to go diagonally through all of these lawns. We're so bad. We end up right there. Okay. What's that?
Yeah, you have to
Yeah.
pick up one.
So we hopped these fences and we just went diagonally through all those blocks. Now I want to know, just like before, this time I want to know what is our final position expressed as a vector. How are we going to do that? What are some options here that we would have?
To make a change. Or square root of 5. Like, that's 2 right triangles. 3 by 3.
Not quite. 4 square root of 5. No. So I want to know, I need to know what this angle is and what the length of that vector is. But the problem is, why is it so much harder?
Right triangles.
They're not, yeah, they're not at right angles, those two vectors, right? So that makes it much more difficult. What could you do? We could. There's some, and you guys are already, see, I figured you guys would probably you'll be solving this in some interesting way here. You're going to figure out some geometric way to do this. And you could. We could come up with, we could do some geometry and probably figure out what those angles are. It gets harder, though, if we extend our trip. Let's say now we're going to extend our trip, and we're not done being hooligans yet. We're going to, from there, we're going to go across through those yards and go over to that house. And then we're going to cross through some other yards and go over here, like that. And that's our final destination this time. So we ran over here, and I don't know what we did. We did something bad. Threw some dog poop on a doorstep or something. We went up here and pulled some other prank, and then went up there and pulled another prank, and then we ended up right there, right?
Getting lunch.
What's that?
That's where it's 73.
Square root of 73, yes it is.
And then the other one is 4 square root of 5.
No, that's your depth. Square root of 9 plus, I don't see how you got that. Square root of 9 plus 9, square root of 18.
2 and 5. 2 and 2.
I'll try that again.
2.
18.
18.
18.
Oh, I just took 10 plus 8.
Yeah, there you go. Okay, so, all right, so anyway, you've already started to kind of see how we could do this. Unless we're able to find some tricky way to, to embed this on a Cartesian plane, though, it gets pretty difficult, doesn't it? Like, what if we ended up, like, in the middle of a yard somewhere or something, in the middle of a block? Then it gets really tough, right? Okay, so what are some ways we could overcome this? What if we were just going to be very accurate and we used some tools of geometry, like say we use rulers and protractors? Is there a way that we could do this?
Yeah.
How could we do it? I mean, you could.
But that's like,
No. Hopefully this really offends your sense of your mathematical ambitions here, because I mean this is really a hokey way to do it, isn't it? And I'm not even going to bother. Normally in a physics class, you would do this. I'm not even going to have you do it. It's so worthless. But we could say, okay, well we're gonna set up a scale here, and let's just say this is 1 block to 1 inch or something, right? We could measure this out. Okay, that's fine. Then we'll measure this vector, right? and well, we already did some stuff here that was kind of useful. What if instead I gave this to you as a story, right? Like say first you're going to go 6 blocks due east, then you're going to go 5.2 blocks at some angle west of north. Well, we could graph all this stuff, couldn't we? We could, if I gave you a whole list of different trips that you took, if I described each one of these vectors individually, you could place them all tip to tail, and then finally in the end, just say, okay, I'm going to start there and I'm going to end there, so I'm going to measure the length of that vector, right? And whatever it is, however many inches it is, it's 1 inch to 1 block, and so we could get a good estimate maybe of how many blocks we traveled, and we could use a protractor and find that angle. So for example, if we were to look at a problem like this one, not that one, like this one. Okay, let's say that I gave you a really convoluted problem where you're going to do all this stuff. We were going to, on a flat field, we're going to walk 25 meters at 49 degrees north of east, then we're going to walk 23 meters heading 15 degrees north of east, and then finally we're going to turn and walk 32 meters in a direction 68.0 degrees south of east. We could write all of those as vectors, right? Connect them tip to tail or head to tail, and then just measure where the tip of the final vector is compared to the starting point of the tail of the first vector, right? Which is essentially what we were trying to do there, right? We go through this complicated network of 4 vectors. If we add them all up, head to tail or tip to tail, then we could just measure from where we started to where the last vector ended up and measure the angle, measure the length, and get an approximation. Hopefully that sounds bad though, right? There's a lot of potential for human error there. It's a lot of work. Is there a better way to do this? Much better way. Much better way. So let's go back for a second to something like this. Let's say that we're going to go back to our first example where we went due east, I think it was 9, wasn't it? And then we went due north 5. And this was our resultant vector. And that's what we call that, by the way. The resultant vector is we get when we add up all of the other vectors. If we're doing it graphically like this, we're just adding them up tip to tail. Okay, did the order in which we went east and north matter here? Of course not. If we went back to that problem, you just as easily, if I erase, I don't know if I want to erase it though, I probably should. So we went all the way over here and then up to there. We could just as easily have gone north first and then gone east, and it has to be the same total distance, doesn't it? Right? Everybody agree? Let's get on the phones and stuff, wait please. Does that make sense? So it shouldn't make any difference. There should be an independence of the order in which we're adding up these vectors. Okay? What could we do you suppose, if we wanted to instead, what if we wanted to pick a harder problem where we're going to go 9 in this direction, and then we're going to go, let's call this a 45-degree angle, and let's say that's a length of 7. I want to figure out where we're going to end up. Problem is, those are not perpendicular to each other. Right? The 9 looked pretty good. That fit really well with our XY plane, didn't it? But this one didn't. The 7 was an oddball. It was not in a convenient direction. Anybody have any idea what maybe I could do to that vector of length 7 at a weird angle so it would play more nicely with the other one? Well, now think about the path. if an ant is crawling along this path, he's going to walk horizontally over to here for his first segment of the journey. Then he's going to walk from there up to there. If all we care about is starting here for his second leg of the trip and ending there, can you describe maybe a different path he could take that would use more convenient directions?
Yes.
What would that be?
Straight back along the path he came.
Ah, okay. What if we broke this vector up into components? If we went backwards, we took the vector and we broke it into horizontal and vertical pieces. Because remember, if we're talking about the trip from, we'll call that for the moment A to B, it doesn't really matter how we get there as long as the vector starts here and ends there. If I wanted to, I could break this up into a sum of 20 different vectors that add tip to tail to go there. That would be not a good idea. But it might not be a bad idea to break it up into two. One that's going to go horizontally that far, and one that's going to go vertically that far. What's the advantage of that? What do you think? Good idea? So if we call this one, let's call this first vector, let's call this vector A, and let's call this one vector B. Okay? If we do that, we might say that this little horizontal piece, being as we're conveniently sticking to the XY plane here, we could call this little horizontal piece down here B sub x. Okay, because that's the x part, or in physics we'd say the x component of our journey from A to B. What are we going to call this one? B, it's part of vector B. We're going to call it B sub y. Right? Does that make sense? Because it's the y part of our journey. We agree? Okay, so we ought to be able to figure out what those are. Okay, if we could, it would be easy to add this up because we could trade this 2-segment journey for a 1-segment or for a 3-segment journey that's much easier to deal with, right? We could say we're going to go 9 in this direction. And what if I just gave you an amount? What if we just said we're going to go, this isn't going to work perfectly here, but let's just say we're going to go, the next phase is we're going to go back in the negative x direction by 4. So we're going to go back this way, 4. Call that negative 4 is our vector then, right? It's in the negative direction. And then we're going to travel from there, we're going to travel up by positive 5. You could tell me the coordinates of that place now, no problem, couldn't you?
Yeah.
What would they be? What would the x coordinate be? What would the y coordinate be? Piece of cake. You probably can't tell me what those are, though.
No.
Right? Until we break it into components. Okay? So the next step, obviously, for us to be able to add up vectors is to break down this little task right there. We've got to know how to take a vector at any random angle and break it into components. Okay? That necessitates a little review of, or introduction to, some right triangle trig. We're not going to do really intense trading here. We're not going to do stuff where we're looking at phase angles and all the stuff you probably did last year in pre-calculus where you're looking at waves and wavelengths and amplitudes and all that stuff. That's not necessary. All we need to really be able to use here when we're resolving vectors like this analytically, adding up vectors analytically, is just SOHCAHTOA. It's just right triangle trig. So let's take a vector, let's just start from scratch with that. And let's say we've got, let's make this nice and convenient in quadrant 1. And let's say we've got some vector out here that has a length of 10, and let's just say that it's at a 50-degree angle. We want to break this into components. Okay. If you remember how SOHCAHTOA works, so here's a SOHCAHTOA. If you can spell it, you can use it. SOHCAHTOA tells us what? If I have a right triangle with an angle theta there. Okay, good. It tells us 3 important things. For any right triangle, if we define, if this is my angle theta, then we have to define the sides of the triangle, right? And this is, how many people, raise your hand if you've done this before. So, most people, but not everybody. Raise your hand if you wouldn't mind reviewing this a little bit, even if you've done it before. Okay, so we're good. So if this is my angle theta, then we would say that the side that theta is looking at across the triangle, we're going to define that as the opposite side. The side that is next to it, our math word for next to is adjacent. So we're going to say that that's the adjacent side. And the side opposite the right angle we always call what? Hypotenuse. Okay. Okay, so then if we want to take this vector and we want to break it up into components. Now, notice that the x and y components, and this is not an accident, they are unique because they are at right angles to each other. This only works if you're taking vector components that are what we call orthogonal, which is a fancy math word for means perpendicular, right? Perpendicular to each other. So if we're going to use Cartesian coordinates in a plane, that leaves us really just one option, x and y. Okay? I mean, that's not true. It leaves us some other options too, but for the most cases, x and y are our best bets. We have to pick two directions that are at right angles to each other. Okay? So then I want to use this SOHCAHTOA scheme up here. This first one tells me S stands for the trig function, and the last two letters tell us what the ratio is defined as. What divided by what. So trig function equals first letter, or the trig function is equal to the ratio of second letter divided by last letter. So this first one says sine theta equals opposite over hypotenuse, right? Okay, we'll wrap this up tomorrow.
That stuff was so much fun last year.
Okay, it was fun.